Okay, good. So, right. We're really happy to have Barak here. He was completed his PhD across the Gulf Coast in University, student of Arnold and Mark Dundry, and is now in Colombia doing a postdoc like many of you. Barak, yeah.
Thanks. So, as Avi said, my name is Barak, and I'm really glad to be back after, I just recently graduated from Princeton University, so I haven't been away for very long, but it's always very nice to be back in Princeton. I'm excited to share with you guys this work. It's going to involve some representation theory, some quantum, some cryptography, but if you don't have any background in any of these, don't worry. I'll kind of take it step by step. So if there's anything that you don't understand, it's feel free to raise your hand and ask questions, because it's probably because there's more that I can explain, not because you're not supposed to understand. So so this is this is talking a lot about different things in quantum, and so I wanted to start a little bit with the basics of quantum, and this is really important for understanding the concepts of this talk is the difference between classical information and quantum information. So classical information, I like to talk about it as it's like the information that you read in a book, right? All the text that you can find in the book. Whereas quantum information, there's a lot of different analogies that people use. I like to use a cake. Wait, this is not quite quantum. There we go. Okay, so classical information, like a book, you can make copies of it. So you can read it, right? You can open it up and take a look inside. You can read it. By contrast, you can taste the cake, but it will destroy your cake. It's one of those cases of you can't have your cake and eat it too. With classical information, like a book, you can make copies of it. Say if you put it in a photocopier. But with quantum information, unless you're a master chef or unless you have the recipe, if I give you a cake and I tell you to make a copy, you're not being able to just make the copy of the cake. With classical information, you can send it over the internet, but good luck emailing a cake. So these are not just arbitrary properties of quantum information. These are actually going to be very, very important for this talk. And these last two are called, this one's called cloning, this one's called telegraphing. And this will be crucial, these will be crucial properties that we will use in this talk. We'll talk more about what they are and how to define them. But first, let me just say the outline. So we're going to talk about quantum money, quantum lightning, and this new cryptographic object that we define called quantum fire. And then I'm going to go a little bit into the more technical weeds about representation theory and how we use it's to our advantage with this duality between two different castes in quantum computing. And then I'm going to show you how to use this to build quantum computing. Let's start with quantum money, lightning, and fire. So what are these three concepts? They might seem like buzzwords, but they're actually quite fundamental to quantum information and to quantum cryptography. So let's start with quantum money. So it has to do with the no cloning theorem. So the task of cloning is to take a quantum state and produce two copies of it. And the no cloning theorem says that if you have an unknown quantum state, it cannot be cloned. If you know some information about it, then maybe you can make another copy. Like if you have the recipe for the cake, you can make another cake. But if I just give you the cake, good luck, making another copy. And quantum money is essentially an idea by Stephen Wiesner, who in the 1960s, all the way back in the 1960s, was a PhD student at Columbia, and thought of hey, how can I use this principle to do some cryptography? And so he thought of this, crazy idea of like, taking photons and encoding them inside a banknote, and then making it so that it's unclonable. And this crazy idea was actually like, it was rejected by publications. So he eventually like gave up, left academia, went to become a construction worker in Israel. But his idea essentially started the whole field of quantum cryptography, and it came to it started all the all like a cascade of all kinds of events that led to cryptography, quantum cryptography as we know today. So what is this quantum money? So we have a mint who knows the banknote, prepares it. So you prepare a quantum state that represents your money, and because the adversary doesn't know the description, doesn't know let's say the recipe for the banknote, they cannot make copies of it. Then if you want to verify it, you can send it back to the mint, and the mint can check whether it's a valid banknote. As I said, this was the first quantum cryptography protocol all the way back in 1968. This is like before most of modern cryptography was invented. He was kind of way ahead of his time, and it was in fact the inspiration for the more well-known quantum key distribution, which actually won the Turing Award this year, the BB84 protocol by Bennett and Barsard. They were actually inspired by his quantum money construction, and thought, hey, maybe maybe we can use this for key distribution, and the rest is history. But in any case, this is like a really, really fundamental object in quantum cryptography. It's the basis of a lot of other objects in quantum cryptography that we deal with, and historically, it's the first one to appear. So it's really important to study it and to see what we can do with it. So one thing that's important to note is that with the version that Wiesner constructed, only the mint can verify the banknote. So, for example, if Alice sends, if the mint gives the money to Alice, Alice wants to transfer it to Bob. Bob can't verify it by himself, so he needs to send it back to the bank. Right? So ideally, Bob would just be able to verify it by himself, and so that's why Bennett, Barsard, Breitbart, and Wiesner later came up with the idea of, hey, what if we add public verification to this? So here just as before, the mint creates the banknote. The adversary doesn't know the banknote, cannot make copies of it, but anyone can verify. Essentially, there's a public verification algorithm that you can just run on the banknote that will check, is it a valid banknote. It's kind of like the equivalent of like taking a banknote and like looking at it in the light and like seeing that it has those little things. I don't know what to call it.
Without destroying it.
What? Yes, without destroying it. So you can verify this without destroying it. And this is useful in so many different cases. It's like it's called quantum money, of course, but money is just a description of it's unclonable. So what is unclonable? Usually we think about money as like you don't want to make copies, but it's useful for anything where you want to be able to verify but not clone. So, for example, if you have a deed to a house, right, which like is a document that shows that you own the house, right? You want to be able to sell it to sell the house, transfer it from person to person. We want to make sure that only one person at a time has ownership of the house. That you can't just like split the deed to like two different people who then claim to own the house. And there's lots of other applications, including like copy protected software and things like that. I don't have to get too much into it, but just know that these are out there. And note that unlike Wiesner's scheme, this is no longer information theoretic because there's a verification algorithm. So if you just run it enough times on just random inputs, eventually you'll find an input that will succeed, right? So you need to have some computational assumptions here. And so this has been a much more difficult challenge to do than Wiesner's original secret key scheme. And so for this talk, I'm going to talk about the public key version of quantum money. So whenever I say quantum money here, I mean the public key version. And in fact, Bennett, Broussard, Breitbart, and Wiesner proposed this idea, proposed a construction. It turns out to have required a discrete log to be hard, but as we all know now, quantum computers can break that assumption, so it wasn't actually a secure construction. Aaronson later came up with another construction that also turned out to be broken, and there's been a long line of proposals that all have turned out to be broken. We'll get to that in the next slide, but before that, I want to talk about a third variant. This is called quantum lightning. This is another type of quantum money, but just now it's collision free. So as before, the banknote creates a banknote, and now even the bank or even the mint cannot produce two copies. So this might sound weird, right? If the mint can produce one, why can't they just run it again and produce the other? So you should think of it this way. You should think of them, each of the banknotes having like this serial number embedded into it. And the process that the mint uses to create the banknote is randomized. So every time the mint runs this process, it will produce a random banknote with a random serial number. And the point is that every time they do it, it will give a random serial number. And there's no way for the mint to produce two banknotes that have the same serial number. And as before, we have the public verification. Anybody can verify. It's a public verification algorithm. As you can see, that this is a strengthening of the public key version of quantum money, because you can show that it's easy to see that if the public could make copies of banknotes, then the mint could produce two copies, because they would just produce one copy and then run whatever attack the public has to make copies, right? And then they could produce two copies. So this is a strengthening of the security of quantum money, and it's security. It's not just against the public, but even against the person who created the money, which is quite a strong security.
So this is again computational? Because
yes.
You could just run it exponentially many times.
This point is a wish. It's something you would want. It's a definition.
Yes. Yeah, we'll get to the construction, but yeah, at this point, I'm just giving the definition. But yes, it has to be computational. This is the question. So yes, it has to be computational because of the verification. Anytime there's public verification, you could just run this verification algorithm, as many times as you want. In exponential time, you'll eventually, happen to come across an input that will succeed.
I guess I meant specifically the fact that mints can't create copies. I was just wondering if they can just exponentially create things until they happen to get it.
Yeah, that's also true. Yeah, because the mint can just run it as many times as they want, and if they're not computationally bounded, they can just eventually hit a collision.
Will they know they have a collision?
I mean, they can
with not pigeonhole. Will they know they?
Oh, that's a great question. Will they know that they have a collision? Yes, because there's a verifier. But if you're talking about without a verification, then I don't know. Maybe not. But because here there's a verification, then they can always know that they're.
So the verification also verifies. It verifies the two things are the same.
It verifies that they both have the same. It verifies that they have the serial number that you expect, right? So yeah. So essentially, whenever you're verifying, you say I claim that this banknote corresponds to this serial number.
And also, I mean, maybe you'll say this when you talk about the actual model, but you're getting this from the fact that the mint does not know the randomness that the algorithm uses. What?
Oh, that's a great question. You're saying that you're asking about whether the mint does not know the randomness that the algorithm is using. And it's actually something quite inherent about quantum computing, that there's inherently random processes. That it's not like there's a random seed that the algorithm is using that's producing this randomness. It's just an inherently quantum process that produces inherent randomness that you just cannot repeat.
I see. So when you write randomized, it's not like a classical randomized algorithm that eventually produces some like quantum thing. It's like you're actually doing, you're doing these unitaries on some state and like you're using the randomness.
Yes. So the question is like, yeah, so it's not just to repeat what you said. So yeah, it's not a classical randomized process where you're like, we have a serial number. It's a quantum operation. You're doing some quantum operation and doing a measurement, and this measurement cannot produce the same result again. It'll have some inherent randomness to it.
The number is obtained by a measurement.
Yes. So the serial number is obtained by a measurement, and you'll never have the guarantee is that if you have bounded time, you will not be able to find collision. So the reason that's called quantum lightning is that there's this phrase that's lightning never strikes the same place twice. It's not true, by the way, but nevertheless, Mark Zandri decided that lightning never strikes the same quantum states twice, so he called it quantum lightning.
This is why it keeps getting broken.
Oh. So yeah, I mean, there has been, as you're alluding to, there have been a lot of attempts at constructing all these different, these two different variants. But we're going to get to this in a moment. I just want to mention a bit of the application. So, why is it called money? Of course, because it mimics some of the applications that we want for money, right? We have two different kinds of money in the world. We have a physical currency, which is like coins, cash, gold, or shells in the ancient past, or any valuable goods where you can just like transfer physically from place to place. And you have person-to-person transactions, right? You don't need any third party involved in the transactions. Anytime Alice transfers her coin to Bob, they don't need to record it with the bank or anything like that, right? But there's physical limitations, right? Like in order to transmit a bunch of gold, you have to have a truck that actually like transfers the gold, or even storing all this gold, you need a ton of storage. And there's no cryptographic security, right? It's just like, the assumption that this is rare or whatnot. There's no cryptographic security that you can prove about this. On the other hand, digital currency, in the modern age, we have all kinds of digital currencies, things like credit cards, checks, cryptocurrency, whatever you have. And here there's these can be transmitted, they can be encrypted, they can be all kinds of data processing that you can do to it. But you have to have a third-party record of every transaction. So with credit cards, this will be like recording with the bank. Every time you pay with your credit card, the bank just records this money transferred from Ellis to Bob, right? Whereas with cryptocurrencies, there's a public ledger that everybody has to maintain, so you have to record. And so this is a disadvantage because you can't just, if Alice and Bob were both on Mars, separated away from everyone, Alice can't just transfer her cash to Bob. Eventually, they need to actually record that the money has been transferred somewhere so that the public can verify. And so quantum money is actually like the best of both worlds here, in the sense that has person-to-person transactions. Alice can just transfer her quantum states to Bob. But she can also transfer it over the internet, transfer it over classical communication, in fact. This is actually, there's actually protocols for doing this now, for doing this over a classical channel. This is surprising, but I'm not going to get into this. If you want to know more about this, you can ask me about it later.
But it's called teleportation.
Even without entanglement, you can do this. So there's ways of doing this where you can transfer this even without entanglement. But these are more advanced things I'm not going to talk about here in this talk. But yeah, so they can be transmitted, they can be encrypted, they can be all kinds of data processing that you want, error corrected, all these things. And so you have kind of the best. So this is the why the world cares about quantum money. We care about it mostly because it's a very interesting conceptual problem that has been open for quite a while, and it's at the basis of quantum cryptography. And in fact, as I said, it's been quite a challenge to construct this. There's been tons and tons of attempts over the last, how many years has it been? 50 something years. to construct this, and unsuccessful because so here's just like a sampling of the attempts that have been made. The ones that are in red have actually been broken. The ones that are in yellow haven't been broken yet, but we don't really know how to analyze them. There's no security proof. They're just like, we have, there's some papers that are just like, here's an attempt, here's a construction. We challenge the public to break this. We have no idea how to prove the security, but we challenge the public to either prove it secure or not. And so we have no really way to kind of analyze them, and they deal with like all these like, mathematics that we just don't actually have a handle on yet. So the ideal would be to have a security proof, like a proof of security that says that, if this, that you can verify the proof and then like this and show that this actually is a secure construction. Of course, we can do this in the black box model. And so there are several cases of this where if you have a black box where you can only see the input and output behavior, you can show that it requires exponential many queries to break. But of course, we don't have any black boxes in the real world. If you want to actually instantiate this in the real world, you need to instantiate the black box with some code or whatnot. And often this actually breaks the scheme because even though it's secure in the black box model, the instantiation is no longer secure. And in fact, in many of these cases, this is actually the case where, this is an instantiation of that one and was broken. This one is an instantiation of that one, also broken. And so it's, a black box security proof is not enough. We want an actual, real world implementation, instantiation in the plane model that we can prove security for. And so this is the gold standard, is the last column here, where we want to show some reduction from a hard problem. We want to show that if a certain problem that we can study, like certain mathematical computational problem is difficult, then it's hard to break the cryptography. What's the money? And here before us, there was only one such case. This was by Mark Zandri, using an assumption called indistinguishability obfuscation. So this is actually post-quantum obfuscation. And this is really, really strong assumption. This is almost like, the strongest that you can think of. Like it implies almost all of the rest of cryptography and more. Almost, there's some exceptions, but this is super, super strong assumption. And in fact, like we don't really know, the quantum security of this is not really clear. So we want some other assumptions where, it's kind of like an assumption that doesn't just clearly imply, almost everything. We want to have an assumption that we can show that if this assumption is secure, if this computational problem is secure, then our quantum money is secure. And in fact, before us, there's no known security proof for the quantum lightning security. So Mark Zandri's construction was only for quantum money. And quantum lightning, it had never been a secure construction. And so we resolve this by having like a new quantum lightning construction. So it's both lightning and money. Essentially a generalization of this other construction from Mark Zandri, from abelian group actions to non-abelian group actions. In fact, this generalization to non-abelian groups is not just like a surface level change. It actually completely changes the things that you can prove about the security of this. So Mark Zandri's construction here required black box access in order to be able to prove security. So the reason it's between them is because he required both black box access and the computational assumption on top of the black box. Whereas we completely remove the black box necessity, and we prove security directly from a computational assumption. And this is a problem with pure action security of group actions, which I'll tell you about more later. Good. So how do we prove security of the quantum money construction? So let me give you a recipe for clonability, for proving computational unclonability, right? So how do you prove that something is computationally unclonable? So you need, you need some task, some like computational task, and we need two properties for it. One is that this task is hard to do if you have just one copy of your quantum state, but it's easy to do with two copies of your quantum state. Okay, so if I give you, we know that quantum states are not clonable, so in general, but sometimes they will be clonable. Sometimes if you have like some information about them, for example, the verification, then the no cloning is not guaranteed. It's like only computational. So we want to show that it's computationally unclonable. So we have some task that if you give me one copy of the state, there's no way for me to solve this task. If you give me a second copy, then now it's just plain easy. And this shows that this state is not clonable, right? Because otherwise you could do it in one copy as well.
This should be true for arbitrary state. You will be able to solve this problem with any two copies of some unknown state.
Oh, so the question is like whether it's like for arbitrary states? No, it's actually for specific states that you care about. There's like some specific states that you care about.
So the no cloning theorem applies to the specific state.
So the no cloning theorem says that information theoretically, if you don't know anything about your state, then there's no way for you to make a copy. Okay. But here, it's not that we don't know anything about their state. If we have some information about it, specifically, we know that it comes from this construction of quantum money, right? That it comes in this quantum money construction. We know that it passes verification, right? We have some.
Why doesn't violate no cloning if you know this information?
So essentially, if you think about the cake analogy, right? It's the difference between if I give you a cake, right, and I ask you to make another copy of the cake, and I don't give you any information.
Quantum states to cakes in this context.
Yeah, sure, but like the analogy is like if I give you the recipe, right? If I give you the recipe for the cake along with the cake, then now you can make a copy, and that doesn't violate no cloning. It's because I gave you the recipe.
And all I'm asking is for the state you are preparing, does the no cloning theorem apply or not?
So it doesn't apply. The no cloning theorem doesn't apply here because you have side information about the state.
So it may be clonable.
So it may be clonable. So yeah, so in fact, all the states that we're going to consider, they're going to be information theoretically clonable. And we want to show that they're not computationally clonable, right? So essentially, like if you were to clone them, then you would have to break some hard assumption, some hard computational assumption. Does that make sense? And so this is how we do this. We have like some task here that allows us to do with two copies. If we had two copies, we would be able to make a computational assumption, but with one copy, we can't.
You don't apply that also the no cloning theorem. You just have a definition.
Yes.
Right? This implies hardness if you believe that this problem is not solvable.
Yeah.
And they can't appeal to the no cloning theorem.
You cannot appeal. Yeah. Sure.
So the input of the task is the state produced by the bank.
So the way that we use this, so you're asking about the way that we'll use this? Yeah, so the way we'll use this is we'll have these states be the banknotes, and the problem will be the assumption that we'll assume is hard. But for now, we'll just like think about it as just like, we have some problem and we have some state that given one copy you can't, with two copies you can. So
this property doesn't imply verification, right? Like that you need to.
Yes, it doesn't apply verification, but I mean, it doesn't imply verification, but it implies the unclonability.
Yeah, it's unclonable.
Yeah. Okay, so the problem that we show that has this property is the problem of testing dirty fixed points. So what is testing dirty fixed points? So we have some a fixed point of a function is you put in an input and you get the same output back, right? You get it just as output, and so if you want to test it, you can just evaluate the function, right? But a dirty fixed point is one where you have two inputs, so you have x, and then you have some garbage other inputs, And it's a dirty fixed point if for some garbage input here, if for some other input here, the first register stays the same. Maybe the other register will be modified, but the first register stays the same. Okay, so so now it's a bit more challenging because okay, what do you put in for the first register?
What do you mean there exists an X? Or there exists a garbage?
So so what I really mean is like find an X, or either find an X or verify that like if I give you an X, right? Maybe I wrote this a bit oddly. But what I mean is I give you an X, right? Ask you, is this a fixed point? Is this a dirty fixed point of the function, right? Now you need to find what to put in to test whether it's a dirty fixed point.
Sorry, the function is part of the problem and X is the input? Like,
Yeah, so the function, let's say the function and X are both part of the input.
I should think of this function as a classical circuit.
So I'm just like starting with the classical function, but what we're really going to do is we're going to switch to a quantum case where now instead of a classical function, we have some quantum operation, a unitary that applies to two registers. So these are both going to be like quantum inputs. This one is the one we care about that we want to state remain fixed. Another one will be modified. And we're asking whether this state here is a fixed point of unitary. And I'm not going to get into the details too much here, but the point is that if you have one copy of this state, there's no way to test whether this actually stays the same. If it were dirty, if it were like a clean fixed point, there's something called a Hadamard test that you'd be able to do to test this. So you can either do this with a Hadamard test or if you had two copies, then you could do something called a swap test. If you guys, for anyone who knows, swap test requires two copies. So whenever you have a dirty fixed point here, you no longer can do the Hadamard test, but you can still do the swap test. So if you have two copies, you can solve this. I'm not going to get too much into the detail because I want to get more into the.
And you say you no longer can do the Hadamard test. Is it a hardness assumption? If you only have one copy, you cannot do it.
So we're going to show that that there's a specific problem for which that has this form of testing dirty fixed point, and this testing of dirty fixed points is hard. We're going to show this based on this security assumption. And given that, we know that this quantum state that's here is unclonable.
And I just want to make sure I get the quantifiers right. When you say it's easy with two copies, you're saying for a particular distribution, or like even this problem in general is for arbitrary is easy.
So if I give you two copies of this state here,
right?
What you do is you apply this unitary to one of them, okay, and then you just test whether it's you check whether it's stayed the same by doing a swap test with the other state. And so the garbage here doesn't matter because the garbage, even though it's modified, now you can just discard it and do a swap test to check whether it's the same as the original state.
Sorry, how do you know what garbage to put in first?
There.
How do you know what garbage to put in first?
So it turns out that like in our case, I think it's okay to have any garbage state. So any garbage state will be fine. The point is that it's modified. I'll get to the actual problem in a bit. All right, so so there's one last primitive that we wanted to talk about. So we talked about quantum money, we talked about quantum lightning, and then there's this new cryptographic object that we define called quantum fire. So what is this quantum fire? So it deals with another a theorem in quantum information called the no telegraphing theorem. So telegraphing is a task of taking a quantum state, converting it to a classical message, and then converting it from the classical message back to the quantum state. And notice that this is not without any entanglement, and so the two parties are not entangled. They just like convert it into a classical message that completely encodes the information about the state, such that they can recreate it. And then a telegraphing theorem just says that if you have an unknown quantum state where you don't know any information about it, there's no way for you to telegraph it. So essentially just impossible to convert it to a classical message. And so this is the idea of like,
why isn't this weaker than no cloning? If I
so-
could have translated the state into data, like classical data, then I have the recipe and I can generate it again and again, no?
Yeah, that's a great point. And this is the next, my next slide is that, yes, so if you can telegraph, as you said, if you can telegraph, then you can clone. So this is the as you mentioned, if you can telegraph, you can convert it to a classical message that you can reconstruct back into the state. So just make copies of this classical message and reconstruct it multiple times so that you can clone. So the no cloning theorem implies the no telegraphing theorem. It turns out that these are actually information theoretically they're actually equivalent. So in these states it can be cloned, can be telegraphed, and vice versa. But
Not computational.
yes, not computationally. And we showed in a previous paper by myself and Mark Zandri that the other direction doesn't hold computationally. Well, it holds information theoretically, but you need an exponential number of exponential time or exponential copies or something to be able to do this.
Under some assumption?
What?
Under some assumption or?
So we showed this in the Oracle model. So in the Oracle model, there's like unconditionally we can show that there's a separation between these two tasks. So if you were to be, if you had the ability to clone, it doesn't necessarily allow you to convert it to classical string.
Are there also like approximate versions of this? Like, could it be the case that I can't, replicate exactly, but I can do, a very similar state where I'm converting it to data?
Yeah, so the question is whether there's an approximate version of these, if like one approximately and not exactly. Yeah, there are versions of this. It gets a bit more complicated there. Let's assume for now that like we're doing it close to perfectly. Maybe it's like with 1 minute epsilon. Yeah, I mean it gets more complicated if you allow a lot of error, but we'll kind of brush that aside for now. So quantum fire is essentially a cryptographic realization of this difference. You have with money, you have a mint that sparks this flame, and then anyone can clone. Unlike quantum money, where you cannot clone, anyone can clone. There's a public algorithm for cloning. So if I give you one of these states, you can give me 2 copies back. As many times as you want, but this flame cannot be efficiently converted into a classical message. There's no efficient way to telegraph. The reason for calling this fire is because like with the flame, if you had like an actual physical flame on a candle, right? Say Avi had an unlit candle, right? I can light his candle, and now we both have a flame, right? He can turn around and give it to the next person and to the next person, and we can make as many copies of this flame as we want. But the moment they're all extinguished, that's it. They're gone. It's in a similar way, you can make as many copies as you want of this quantum state. The moment you measure it, convert it to classical message, is gone. Can't be recreated. And so there's several, like with quantum money, there's several versions of this with different security levels. There's the secret key version, there's a public key version, where there's public verification. There's a randomized collision-free version. I'm not going to get too much into those like different variations, but just know that it has all the different variations that quantum money has. Yeah, so previously there is no known constructions in the plane model, or even in with any even a proposed construction. So the only construction that we had previously was by a work of myself and Mark Zandri in 2023 with a unitary quantum oracle. Here we propose the first candidate construction that uses a classical oracle. Yeah, unfortunately, we didn't prove the security, but we give like a plausible way that you can construct it in a way that you can actually make clones of the state, but it's plausible that you cannot telegraph.
Any applications of this object?
Oh yes, applications of this object. So yeah, there are applications of this object. There's applications for verifiable entropy or verifiable randomness. There's applications for something called key non-exfiltration, where if you have a server that's interacting with outside world, key exfiltration attack is if you were able to send a virus that takes over the server and then sends the key outwards to an outside adversary. And so you can imagine taking this the server and instead making it a quantum server, still doing the same cryptographic tasks for its clients. The interaction with the outside world is still classical. Now it's a quantum server. And now you can have the cryptographic key be a quantum fire state. So it can make copies as many times as you want to be able to run in parallel with, like, say it has millions of different clients, it can run in parallel with to service all those millions of clients. But if an adversary were able to take over the server, they wouldn't be able to exfiltrate any of the keys because of the untelegraphability. And you can find out and shut down the server, and you're guaranteed that it's secure from that. So yeah, so there's several applications, and there's others that have like in other papers that people have written since. But yeah, so a priori, it's not clear that you can even do this, right? Because how would you enable someone to copy the state without actually knowing the description, right? Because one way to do this is to allow them to take the quantum state and convert it to a classical message, as we saw, and that allows you to clone. But we specifically don't want people to be able to do that. So we want them to just go directly from one quantum state to two copies of quantum state without ever going through a classical intermediary. And we showed that one really interesting way to do this, where you essentially start with quantum state and an empty register, and you start by entangling them, the two registers. And then in the first step, and then the second step afterwards, you disentangle them and you end up with two copies. And because this entangling operation, as you can imagine, cannot be done over a classical channel.
But it also has to apply to a specific set of states.
So
it has to be applied to a specific set of states.
Yeah, so
not every state, because we know that's impossible.
Yeah, exactly.
So this information is always.
So the cloning, so as I said, it can't be applied in general because general states cannot be cloned. We have a specific subset of states where these states can be information theoretically cloned, right? But not only information theoretically, but actually efficiently can be cloned. So there's an efficient algorithm that allows you to clone them. And the point is that, we hope that there's no efficient algorithm to telegraph them. And this we leave open, by the way. So unlike for the quantum money and quantum lightning, where we prove cryptographic security, here we essentially propose just a candidate, the first candidate construction.
Can you say again that intuition you gave with entanglement?
Yeah, and maybe I can describe it more offline, but essentially you take a quantum state and you have some entangling operation, and then you have a disentangling operation. That's over the process of it, these two registers become entangled with each other, and then you disentangle them in such a way that now they're two copies of the original. I can give more details later. Okay. And in fact, there's later work that came right after ours, that built on our idea and using very very different technical tools, so very different construction. Gave a classical Oracle construction with a security proof of quantifier. So we now have actual constructions of this that we can use. Okay, so we've talked about quantum money, lightning, and fire, and now I want to talk a bit more about the technical details and some really really interesting conceptual things that happen behind the scenes. So this is with a computational duality between two different computational tasks. So this is something that started with work by Aaronson, Atia, and Susskind. This is so these might be unusual names to see together. So right, like one we have a computer scientist and a physicist, right? Where they're writing a paper together. Essentially they were trying to study the complexity of black hole and like black hole operations, and they came across this really interesting computational duality between two different tasks. One of them is called the swap task. It's an unfortunate name. Unfortunately, I didn't give the name. I would prefer the flip name, but this essentially you can think of it in terms of cats, right? This is actually how they describe it in their paper, so I'm going to use the same terminology. So you have cat that's either dead or it's alive, and the task is just to flip the state. It's like flipping a switch, right? So if it's alive, convert it to a dead cat. If it's dead, convert it to an alive cat. Okay.
One side sounds easier than the other.
Yeah, very much, yes. So, but you can imagine, like, instead of an actual cat, there's actually like, some states in your computer, right? Okay. And the distinguishing task, so notice that it's the same operation. So the swapping operation or the flipping operation does it with the same operation, right? So you have an operation that goes back and forth. There's the same operation that flips the switch in either direction, right? So you have a unitary that if you put in a live cat, it unalives it. If you put in a dead cat, it brings it back to life. And the other task is the task of distinguishing, where you have a Schrodinger cat. So Schrodinger's cat is kind of a cat that's in superposition of being both dead and alive at the same time. And so this is represented by alive plus dead. And there's actually another, two different ways that it can be in superposition. There's actually more than this, like two important ways they can be superposition. It could be alive plus dead, or could be alive minus dead. And the task of distinguishing is to distinguish whether it's in this superposition or that superposition.
You distinguish, but what is given for the distinguishing state?
So
U is given, or
so the task of distinguishing, you're just given like either this superposition or that superposition. You're just told which task.
What do I know about the cat? I know about the state. Like, is there a state input as well? Like.
So
I mean, like, can I change coordinates such that they, right? Like,
so this will be a computational task, and you'll be told in some way, like, what the actual like things that you're distinguishing between, but it might not be like it might not be an easy description. It might be, for example, these are outputs of some circuits or something like that.
what is the role of U?
Oh, so this is only for the swap task. So there's two different tasks, right?
you want to find the U, right?
So for the swap task, it's like finding like implementing a unitary, implementing an operation that's like this flips the switch.
Given this state?
No, not necessarily given the two states. It's just like you're given one of the two, and you flip it to the other. With some description, you have some description of like what the task is, right? I'm being a bit informal, I admit, but
you know what the two possible states are.
Yes,
so given one in some way.
Yeah, they're
You want
given to you in
to
some
flip
way.
it to the other one.
But yeah. So yes, you know about it in some way, but it's not like you're given copies of the state. You're just like, you have some description in some form, right? This is like a broad class of tasks. This is you're given some description of like what alive and dead is.
It's important what the description is in both cases.
Sure, but like whichever description you have will affect what the complexity of these tasks are. Okay? So whatever complexity this task has is like it depends on your description, it depends on like the states that you've put in, but like you have two states and the task is this is like a kind of generic task of just like flipping between two different states. This is a generic task of distinguishing the two superpositions. And so Aaronson, Atia, and Susskind showed that essentially these two tasks are computationally equivalent. So given the ability to map between these two states, you can distinguish with their superpositions, and given the ability to distinguish superpositions, you can map two states. And they used it to kind of argue why we don't see Schrodinger's cats, right? It's a technical challenge to like actually make Schrodinger's cats to like put cats in superposition. But they argue that even if you had a Schrodinger's cat in front of you, even if you had a cat that's simultaneously both dead and alive in front of you, you will not be able to actually tell that that's the case. Because in order to be able to tell that it's actually in superposition, both being dead and alive, you need to at least be able to distinguish whether it's like in the superposition versus just like a mixture of like, 50% being alive and 50% being dead, right? And it's just like randomly chosen one of the two. And if you could distinguish between like a superposition and this like mixture where you have like, just randomly 50% probability of alive or dead, then you could use this. It's not hard to show that you can use this to distinguish the two different types of superpositions. And if you can distinguish the two types of superpositions, then you can flip the switch and you can resurrect the cat. So they call this, I think they call this necromancy part in the paper.
How does the double slit experiment distinguish the randomized from the quantum? Right? I mean, you look at you shine a light and you see what comes out. If it was random, it would go only through one of them.
Yeah.
If it's quantum, it goes through both in superposition.
Yeah.
That distinguishes
Mm-hmm.
the randomized and the quantum.
Yeah, so that's a great point. So yeah, with things like photons and electrons and small particles, we can actually like distinguish whether they're in superposition or not. We can do like measurements to distinguish these. And we can also swap. We can also like flip the states of these electrons or photons, right? So either both of these tests are easy, which is like the case right here, or if you have something really complicated like cats, say, right? Cats is quite a complex structure. So in that case, the argument is that both of these should be hard. And in fact, the complexity of both of them is always going to be the same, up to like some constant factors. This is not just like a philosophical exercise. This has been really, really important in cryptography throughout the years since, because you can think of one of these tasks as a search problem, and the other one is a decision problem, right? And these are the two really important tasks, types of tasks that we have in complexity in cryptography. And it's been used to show a lot of different search decision reductions in quantum cryptography and in quantum complexity theory. So it's been, even though this is a very simple principle, it's actually quite easy to show that, like, that they each imply each other. It's a short proof that in my direction, but it's kind of like the principle of like looking for this duality, looking for this equivalence, allowed researchers to just see this, and once you know about this principle, you start seeing it everywhere. Every time you just like see like, oh, I need to show the hardness of like flipping from this to this. Then you can like switch it to showing the hardness of distinguishing these two superpositions, or vice versa. And it's just like once you just like have this in your head that this is the phenomenon to look for, then it starts popping up everywhere you see. And it's been quite influential in showing this is just a sampling of the results in like search decision reductions that have been based on this kind of principle. Okay, so what we do here in this work is we generalize this. So we generalize the first one to what's called a group representation. I'll tell you more about this in a second. And the second one we generalize to.
We know better group representations than quantum money. So
What?
I'm joking that we know better group representation than quantum money.
Oh, okay. So maybe we can not spend too much time on this, but the other one is the Fourier extraction. And so we show that these two tasks are computationally equivalent, much like they are for the original case. And in fact, the Aaronson Atia Susskind swapping distinguishing duality is a special case of ours for when you take the representation of the group Z2. And so this is a generalization of this principle, and it comes in quite importantly in our security construction. And so let's start with the group representation. I'll tell you everything you need to know in a short slide about representation theory. Representation theory is quite a deep subject, but this is essentially the main ideas you need to know about. So representation of a group is just like maps it into the unitaries. So we're talking about unitary representations where you have like matrices for each group element. So for example, say for each group element G, you have some matrix corresponding to it in such a way that it preserves the group operation. So when you multiply the matrices, it's as if multiplying the group operation, doing the group operation. And one important thing that you might want to consider, and this is one of the important concepts in representation theory, is diagonalizing these unitaries. So if this were an abelian group, if all the elements commuted, then all these unitaries can be simultaneously diagonalized by the same isometry. But when you have a non-abelian group, then now there's no basis that will simultaneously diagonalize all these unitaries. So the best that you can do is block diagonalize them in a form like this, where you have these blocks here on the diagonal, and they might be non-zero here, but zero everywhere on the diagonal. And every group representation preserves some set of invariant subspaces. Inside these blocks here, each one corresponds to a subspace. So if you start in one of these subspaces, you'll continue to be inside the subspace. And you can label these invariant subspaces by different lambdas depending on which matrix appears here inside the block. So there'll be like very specific unitaries that can appear here, very different specific representations. These will be called irreducible representations. If you want to, I can talk more about representation theory later. But this is essentially what we need to know is that we can decompose this into we can decompose it like this, where we have multiple copies of a specific unitary, and then maybe copies of another specific unitary. Each one of these will be an irrep, and then it will be labeled by some irrep label length. And then we can name which copy it is and which basis vector inside of it. And I think one thing that I want to get across is that, what is the unitary? What is this unitary V here that we applied in order to block diagonalize this? This is the Fourier transform. It might not be the form of Fourier transform that you're familiar with, but this is a very clear generalization of the standard Fourier transform that you're familiar with to any representation. So the way that this actually shows up is that if you take if you take any group and you take what's called the regular representation, and then you apply this isometry to block diagonalize it, this is the Fourier transform of the group. So this is like, the Fourier transform of a group is a special case of this, and the Fourier transform that you might be used to is when you take the group, Zn or something like that, or if you take the real numbers and
the hypercube.
What?
The hypercube.
Sorry, the hypercube, yeah. So these are all special cases of this, but you can do this for any representation. It's not always just the regular representation. Any representation you can take, you can do a Fourier transform for that representation.
So what are you calling the Fourier transform exactly? This
The diagonalized.
Change of braces.
Yeah, the
there are
diagonal.
many such Fourier transforms, right? Like
yes.
you can, like any subbases to these invariant subspaces, you can pick. You can also permute them. You can, like there's many.
Yeah.
You want the components to be irreducible.
Yeah, but still there are some permutations.
But you can
So there are many,
you can choose
Any,
you know any basis, even if there are isomorphic components, you can do like there's a lot of degrees of freedom here.
Yes.
Yeah,
That's a
but
good
you
point.
want to know, just you want to be able to
So
label
is the Fourier
them.
transform any such thing, or
Yeah,
is
so
it
there's,
just
like,
the
multiple-
invariant subspaces?
Yeah, so just to repeat, like you're saying that there's multiple possible choices that you can make how to block diagonalize, and that's true. The Fourier transform is not uniquely defined. It's it's uniquely defined up to some up to some equivalences. As you can say, as you said, you can permute between the different blocks. You can apply unitaries inside the blocks. You can if you have like multiple copies, you can apply like the transformations within the copies. So there are some degrees of freedom that you can choose. The Fourier transform. When I say the Fourier transform, I really mean like choose one of those degrees of freedom, right? And so, it might be in an arbitrary way, but like up to those degrees of freedom, it's uniquely defined. And it's essentially the unitary that optimally block diagonalizes this, right? So you want to make sure that there's no there's no blocks here that can be further subdivided. And so, how do we think of this in a quantum sense? We think of it as like we have some state here, and when we and this is a state that's going to be a state that's acted on by these unitaries. And what we want to do is we want to kind of transform it into a basis that contains the irrep label lambda. It contains the multiplicity index, which is like telling you which copy of the same irrep here, and then you choose some basis inside. And just tell you, some index for that basis. And if the state has a definite irrep and multiplicity, I'll often just like draw it as if it were inside the block. Of course, it's in the subspace corresponding to the block. And when, for example, the group Z2 is the case for the Aaronson Atia Susskind duality. And here you can see it as like take the two elements 0 and 1 in the group Z2, and 0 you represent as the identity. This is always efficient. And the 1 you'll represent it by this unitary that does the swapping operation. And this is a representation of the group, because if you do, if you swap twice, it will go back to itself. As you can see. And essentially the Fourier basis will be this basis of like the positive superposition and the negative superposition. And so applying the Fourier transform will get you between these two. And the point is that even the Fourier transform for the group Z2 is efficient, right? It's easy to do the Fourier transform for the group Z2, but a representation of the group Z2 may have a Fourier transform that's inefficient. So they're making a distinction between the Fourier transform of the group and the Fourier transform of the representation of the group. And in this case, in fact, the Fourier transform here is non-efficient. Or depending on which swapping operation you choose, right? Depends on that, but it's not generically. Okay, so that's the group representation. For extraction, I'm gonna like glide a little bit through the details here because I think they're just somewhat technical and we're low on time. But they're essentially this is essentially generalizing the idea of something called Fourier sampling or Fourier measurements, where you want to measure in Fourier basis. So the ideal functionality that it's trying to imitate is if you take a quantum state and you want to just like do a Fourier transform on the state, of a representation that applies to the state, and then just measure what the output is, and In this case, for example, it would be like measuring between plus or minus. And it turns out that for abelian groups, this is equivalent to a different circuit where you flip the circuit upside down. And instead of doing the Fourier transform on the representation, you could do the Fourier transform on the group itself and do the operation the other way around. And these two circuits turned out to be equivalent. And now the side on the right, this is efficient, right? Because it might be the group Fourier transform is efficient while the representation Fourier transform is not. So you can do this circuit on the right, even though you can't do this circuit. But you can implement this circuit by doing that one. This is a generalization of some property that you might know from if you take in like intro quantum, where you can like flip the C naught by applying Hadamard's to it. This is called the Fourier sampling circuit, and we can generalize this to non-abelian representations. So in non-abelian representations, there are going to be like two, there are going to be three wires for the three different parts of the Fourier state. And so, it turns out that these are no longer equivalent. These two circuits are no longer equivalent. You can implement one with the other, but not the other way around. So if you want to actually...
What does these many lines from zero mean?
It means that you have something in the Fourier basis where the first one is going to be maybe the irreducible, the second one's going to be like the multiplicity maybe. Okay. The third one is going to be like the basis vector within the
but it's still for zeros.
It's going to, so for this, let's assume this is like the identity element of the, or like, not the identity element, this is going to be the trivial representation of the group.
Yeah.
So we start with the trivial representation.
You don't have any.
Yeah, exactly. So I guess these are not there. Yeah. So, sure. So, so you can generalize this circuit, and you can generalize this functionality, but turns out they're not equivalent. Right, you can implement this with that one, but not the other way around. If you want an actual equivalence, you need to modify it a little bit, and this is the Fourier extraction. And now, instead of making copies up to your state that you get on the top wire, you're actually doing this kind of swap. You're swapping the wires. And this is essential to get it so that these are actually equivalent. Turns out if you want it to be actually equivalent, there's a little bit more that you have to do, but this is essentially the picture. There's this principle in quantum information called the phase kickback, where if you in one direction you apply an operation from this register to that register, in the Fourier basis, it's like in the opposite direction. But this is kind of a state kickback. This is like where instead of like just copying a phase over, you're actually moving this state itself into the outside register. I'll skip a bit more in the details of the Fourier extraction, but it's essentially an operation that measures the subspace that you're in and coherently recovers measure the irreducible coherently recovers the state. You can think of it like you have a state inside one of these subspaces, and now you're just like bringing it into the standard basis. It's not just having it in your hand.
So in the abelian case over the cube, you just generate a uniform superposition on all characters, and then you measure it, and you know one thing.
Yeah. Yeah. You actually just start with like the trivial.
Yeah. Then you apply. You generate this out by quantum Fourier transform.
Right, and then you have the superposition over all the group elements.
And then you measure a curve.
Mm-hmm. Yeah.
Curve innovation.
Yeah.
So that's the generalization.
So this is a generalization of that.
But wait, you exactly, then the C naught is important, right? It's exactly flipping a plus to a minus somewhere, right? Exactly in the correct place, such that when you do the Fourier transform back, you get the actual representation, right? So we're trying to recover the Fourier transform of the unknown representation, right?
So we're trying to do like so in some sense this Fourier extraction is for a case when maybe the Fourier transform of the representation is inefficient.
Yeah.
But the Fourier transform of the group is not. You can't do it efficiently. So yeah, this is kind of the next best thing to do in the Fourier transform representation. And so yeah, so unlike
so after you apply, you take the previous state, you generate an appropriate superposition for the irreducible representations. What is the operation? What's the analog of the C naught?
The analog of the C naught it would be like a group representation. Yeah. So if you can do the group representation here, right, and you could do Fourier transform on the group, not on the representation, right, then you could do this Fourier extraction. It's not as good as if you were just able to do this for the Fourier transform on the representation, right? But it's the next best thing. It allows you to both recover the irrep label. It allows you to recover the state inside the subspace. The only thing that's different is that you don't get the multiplicity in the clear. You get some encoded version of the multiplicity that will no longer might be hard to access. So it's kind of the next best thing to do in the Fourier transform. Yeah, so this multiplicity, this encoded state for the multiplicity is actually quite important. It's, we call it the archetype state. And the important thing is that it only depends on the subspace that you're in and not on the state within it. Because the information about which state you're within the subspace is extracted to this register. It's completely swapped out. So whatever is left here is completely independent of the state that's inside.
The extracted state is the matrix coefficient.
Say again?
The extracted state is the matrix coefficient.
No, so the extracted state here will actually be like a quantum state. It's a register that contains the quantum state. So it's actually going to be like an actual quantum state that you get. You guess whatever was inside the subspace. You have superposition in the subspace. Now you have the superposition over, let's say, the basis vectors 1 through k. Where k is the dimension of the subspace.
It doesn't know which copy are in.
Yeah. Mm-hmm. And so the archetype state will actually encode which copy of the subspace you're in. This allows us to do this this allows us to do the dirty fixed point thing because we have this task of the same versus different subspace, where essentially what we can do is we can test. So the problem is given two states that are either in the same subspace, right? So say you have two different, multiple subspaces that are identical otherwise, but you have two states that are either in the same subspace or they're in different subspaces, right? If you have just one copy, right, and I took your state and I moved it to a different subspace, you wouldn't be able to tell that I moved it, right? But if I give you two copies and I move one of them from this subspace to that subspace, you can test it with a swap test. So this is a dirty fixed point problem. And this is the way that we recover this dirty fixed point problem, which allows us to prove the security. This completes this recipe. Essentially we have this.
So for billion groups, you have a quantum for the transform, and you have it for the symmetric group. What's other you are using specifically to some group?
Oh, yeah. So
billion groups you don't have multiplicity, so this will not be
great. So this is essentially requires you to have a non-abelian group, and this is why we, in our construction, we move from Marx Endry's abelian construction of quantum money to the non-abelian construction.
The non-abelian is different than just for the symmetric group. You apply to other group or which group?
Yeah, so we can show that for any group which satisfies the security property that the pre-action security property that we have. That if you apply this, if you have a representation of this group that you can efficiently implement, then you can build quantum lightning from it. Quantum money and quantum
we don't know other non-abelian group except the symmetric group, I guess, for which we. So yeah, so there's besides things that are very short term.
Yeah. So there's a so you can use a symmetric group. You can use there's some other groups that are non-abelian groups for which we know efficient Fourier transforms for. And the point is that you need an inefficient representation for which the Fourier transform is inefficient, right? And so this is what the group actions are.
So you suggest some concrete
Yes.
group and the representation which you believe is how to implement.
Yes.
Yeah.
It's not that the representation is hard to implement, it's a Fourier transform.
Oh, yeah. You tell us.
Yeah.
Okay.
So just to conclude here, we have these two tasks that are computationally equivalent, the group representation and the Fourier extraction task. And the last thing I want to do in the last minute, how much time do I have left?
-12.
Oh, okay. Should I continue and finish in 5 minutes? Okay.
We are happy with the extensions, but
Okay. So we're using a specific representation. It's called the cryptographic group action. So what's a cryptographic group action? A group action is a way that you can use a group to act on some set in such a way that it like maps a certain set element to another set element, kind of permutes between the elements of the set. I mean, I like to think of this as in terms of Rubik's cubes, because this is like a place where people commonly have like an intuition for these like non-abelian group actions. So you can think of the group as like all possible transformations all possible moves that you can do in a Rubik's cube, and the set is just like all possible configurations of the Rubik's cube. You apply a move to a configuration, it gives you another configuration. And in order to make it a cryptographic group action, there's a few things that we want. One is that we want to fix a starting element. So for example, like the solved cube maybe is the starting element. And that's so that when we have algorithms, we know where to start from. We have some set element that's like, it's picked out that we can start from. And we want to assume that every pair of configurations has a unique group element that maps between them. And there is a way to generalize this for cases where that's not the case, but let's not get into that here. Let's just assume that every pair of configurations has a unique mapping. Yes, so this is a faithful representation. Yes. And in order for it to be cryptographic, we want cryptographic hardness, and the cryptographic hardness is usually that it's hard to find this mapping. So there exists a mapping. So if I give you two configurations, there exists a mapping, but it's hard to find. We're going to need an additional assumption on top of that, a slightly stronger assumption than that. And this is, involves the concept of pre-actions. So an action takes a group element, applies it to this element to get another set element. But since we have some starting element, we can take every configuration and write it as some operation applied to the starting set element. And so we can kind of write it like this, right? And so when you apply your group action, what you're doing is you're appending another group element to the left. So you're post-scrambling. It's like I already have a scrambled Rubik's cube, and I'm scrambling it a bit more. On the other hand, pre-action is a way to it takes a group element and takes a configuration, which again we can write it in this way, and pre-pends a group element. So this is like pre-scrambling. This is like I took a Rubik's cube, I scrambled it for you, and now I tell you, okay, make this move before my scrambling. Right? If you could unscramble it, then sure, you can unscramble it, make the move, and then re-scramble it, right? But this should be hard, right? In general. And so, and by action here.
Clearly the abelian case is easy, right?
Yes, so that's a good point. So if you have so in the abelian case, the pre-actions and pre-actions are the same, and so there's no hardness here. And yeah, this is like one of the reasons why you actually move to non-abelian group actions. There's several reasons that I mentioned, but this is one of the reasons why this wouldn't work in the abelian case. And a bi-action is both an action and a pre-action. And pre-action security comes in two different forms. There's a search version and decision version that we define. The search version is called pre-action hardness. It's hard to implement a random pre-action. And the decision version is that it's hard to distinguish random actions from random bi-actions. So say if you give me some set element And this is through an interactive game. You give me some set element. I either apply an action, random action, or I apply random action and pre-action. And you need to distinguish which one. And as you know, like pre-action security only makes sense for non-abelian group actions.
So when you say by action is both an action and pre-action, are you saying like HG equals GH inverse?
So you take we'll take two group elements, apply one prepend and postpend, right? Okay, like your input is like two different group elements now, and you're both prepending and postpending. Okay, so how does this give us quantum lightning? So the banknotes here are going to be any state within one of the invariant subspaces of the group action. The group action's representation, you can break it down the same way. We're going to give some states within one of the subspaces. And the serial number will just be the Europe label. It will look something like this. I don't want to get into too much the details, but this is like the form mathematically of these states.
But here it's very important that, wait, I want to understand this. Sorry that I'm stopping. We had these special like you had this action, pre-action thing.
Yes.
Like they clearly define a representation of the group.
Yes.
And then you choose it like the representation such that this task of pre-action is hard, okay, right?
Yes.
And then you know that like doing this V is somehow hard. That's what you're assuming, right? That this V is somehow hard to do on your own.
Yeah. And not only that, we want to show that this like distinguishing this same versus different subspace distinguishing task is hard. And we can show this from the pre-action security.
Okay. No, you said the group action here in the Brown notation. So the group action is just the action from before for which we know the like pre-action is how.
Yes.
That's the only thing.
Exactly.
Okay.
Yeah. And the states look like this. I mean, if you don't in representation of theory, don't worry about the actual form, but you can think of like the cyclic group example, it would be like this. But yeah, I mean, I wouldn't worry too much about this. You can't use a cyclic group. We need something non-abelian. And in fact, we show this from using a group action of a symmetric group. But you can choose a bunch of other ones. So there's a bunch of other, whatever pre-action you choose, whatever group action you choose. If you show that it has this pre-action security, then it's a good one. Okay, so the verification would just be perform a Fourier measurement on the claimed banknote to just check that it's in the correct lambda. You're not checking which subspace, which copy of the subspace it is, just that it's in the correct Europe label. Minting is just the same thing, but you just perform Fourier measurement on the starting element. So you just take the starting element and you can rewrite the starting element as the superposition. Turns out that you can write it as a superposition of all possible Fourier states, which means that it's just all possible banknotes. Once you measure it, you get a random banknote. This is interesting.
Why when you measure the lambda, you don't destroy this path?
Yeah, why when you measure lambda, you don't destroy it?
You will know lambda. Right?
Yes. And the reason is because all our states will always be in a fixed Europe label. So when you measure the Europe label, you will have a different outcome.
Then that means that this is not the banknote number, right?
So the lambda will be the serial number. So the serial number, the banknote number will be like
which Europe you're in is the serial.
Okay, so every representation will give you only one banknote.
No, because it will have multiple Europes possible, right? The representation will have lots and lots of different Europes. We'll actually need groups that have like exponentially many Europes. Yeah. And each one of those Europe labels will have like a...
Fine, but once you measure it,
you don't destroy the money because like
you don't you
don't destroy because it's a part which is like a constant. Like once you project it,
per representation.
Yeah.
But aren't there only n representations of your group?
N is exponential.
Yeah, so we take some like, for example, a symmetric group on like little n things, which will have like exponentially many like possible pairs. Yeah, so you can like each time you do this, each time you mint, you will get a different irrep. Like you'll just randomly get some irrep. And in fact, because it's a position of all possible irreps, you'll get like each irrep with like a negligible probability, and so you're not likely to get the same irrep twice. And yeah, I mean, this is like hand wavy, but we actually show this. Okay, so the theorem is that if this group action is pre-action secure, then this is a secure quantum lightning and quantum money scheme. Okay, and I checked the paper for more things. We have an approximate duality theorem. We also have show that we can construct it from symmetric group actions that appear in the Michaelis crypto system. Note that this is not security from the Michaelis assumption necessarily. It's that there's a group action within the Michaelis crypto system, and if this group action is pre-action secure, then our construction is secure. And so it's slightly independent of the assumption actually in the Michaelis crypto system, but the point is that like this is actually a well studied mathematical like group action, and so it's unlikely that this can be the pre-actions can be broken here. Yeah, we also have like quantum other candidate constructions, and you'll see that. Right? Thank you.
We have more questions.
I guess you said you didn't want to talk about this, but you mentioned that like you could have quantum money where you could transfer it over a classical channel. Can you say anything about that? Or
yes, so so transferring quantum money over a classical channel. So you can't necessarily do this with this construction, but you can do this with construction from where you have a construction from indistinguishability obfuscation. So there you can have construction of quantum money and quantum lightning. This is a newer work that's where you can actually, transfer it interactively over a classical channel. So suppose that I have a quantum money state, you do not, right? How could I transfer it to you? What you do is you send me a classical string. I use my quantum money state to kind of sign this classical string, destroys my quantum money state. I send you the signature back, and now you can use the signature as like the signature allows you to have a new quantum money state now you have. It's using this thing called one-shot signatures, where you can you can have these states where you can sign one thing but not two things.
And that was only recently constructed or something, right?
Yeah, it was recently constructed after our work. Yes.
So this quantum money doesn't have this zero number.
It does.
It will be a different state. It's not like the same state you have, right?
Yeah. So the guarantee for quantum money is not that necessarily you have to make an exact copy, but you just need to make another state that still verifies.
Yeah. So
passive
this is
verification.
quantum money, not the lightning. Yeah.
So it actually gives both quantum money and quantum lightning. In both cases,
Lightning is just that you cannot mint the same thing twice. So it's okay that it changed. It's not the same lightning. Yeah, that's okay. You can transfer something which is a new lightning. It's not the same lightning.
Yeah, but it still passes verification. It's like you allow all the different states to all pass verification for the same serial number. So the point is like, if you have a state that corresponds to a certain serial number, you can transfer where like Alice gives Bob another state, not necessarily the same state, but corresponding to the same serial number. But at any point in time, only one person at a time has a state that has the serial number.
How is this soundness proved?
How is the soundness proved?
Yeah, like how do you prove that you won't be able to sign the letter without destroying your state?
Yeah, so this is like this is not our work. This is a different work, but this is using something called indistinguishability obfuscation. It's like you have some obfuscated circuit, and this it's a so you can use this to build these kind of one-shot signatures. Maybe we can talk a bit more offline.
Oh, maybe one more question. So you guys seem like you and other people have constructed these amazing primitives, right? I guess how are people like surprised that these primitives exist, or do they think that they should exist? And then the question is how to construct it. Like, what is the psychology of the field?
Yeah, so I think for quantum money and lightning, the general feeling is that they should exist, and we've just been struggling to build them. I think more and more, as I showed, there's a long line of works that have tried to construct them and failed. Each one, the fact that there's so many attempts, kind of shows you that people believe that it should be possible. But the fact that they each one of them failed, some people are like, okay, well maybe there's a reason why they all failed, and it's actually just not possible to do this. I think we're pretty convinced now that this is actually a real thing. But so we give a plain model of construction using some assumptions. Now they're constructions using other assumptions after our work. And I think it's pretty convincing now that these things probably exist. But the assumptions that we have here are still strong. Somewhat strong. So if we can build them from
the pre-action, you think of the pre-action assumption as a strong thing? It doesn't sound it sounds very natural.
Particular groups, yeah, maybe we don't know. I don't know if people thought about.
You say it's just
it's not obvious that quantum algorithms factor into them.
Right. Yeah. You say until there's an algorithm, we're kind of blind of whether it's.
I don't know how much people thought about this.
You would expect a reduction from some other more classical thing to.
Yeah. So the ideal, I think the gold standard, if you could show a reduction to something like LWE, I think that would be amazing. We have made some attempts to connect this pre-action security with LWE. There's some technical reasons why it hasn't worked yet, but ideally we'd have just a reduction directly from LWE from something like that. That's more standard. Right now we have it from this pre-action assumption, and we have it from this indistinguishability obfuscation. So indistinguishability obfuscation is a really, really strong assumption. I'd say too strong, but nevertheless, it's commonly believed that this exists. But yeah, it would be nice to build it from weaker assumptions. In fact, it's a really interesting situation that we don't even know how to show that this can't be built from one-way functions. It's entirely possible, consistent with existing knowledge, that these objects can be built from one-way functions.
But you also said there are newer paper that provides construction with weaker assumption. Can you see?
No, not from weaker assumption, from really strong assumption, from indistinguishability obfuscation.
Okay, so these are only few constructions right now.
As far as I know, they're the only ones that are actually provably secure. The other constructions that are there's constructions from knots, for example, that are just no security proof, or just just a construction, but it's just open whether it's actually secure. These are the only constructions that I know of that are provably secure. And the thing is, it's entirely possible that consistent with current knowledge, nobody has shown an impossibility that it can't be constructed with one-way functions. It seems somewhat unlikely that you could do this because we don't even know how to build it from really, really strong assumptions. So it's kind of a huge gap of in our knowledge currently about what are the assumptions necessary to build these to build quantum money, quantum lightning, quantum fire.
Okay, thanks.